and welcome to our webinar today with the title Moisture in PCBs, Development of an Efficient Drying Process. I'm Andreas Schilp, your host and as well speaker of today's webinar. And now I wish you a lot of fun and new information. The aim of this webinar is to develop an understanding of moisture in materials, especially in printed circuit boards, to know the effects of further processing and to be able to derive targeted corrective actions when moisture-related problems occur. In principle, the considerations are valid for all types of PCBs, although these basic principles are of particular importance when working with flexible and rigid flexible printed circuit boards. Observing them can mean the difference between success or failure. So these are the points I will present today. We are starting with when is moisture in printed circuit boards critical? Then we have a look on documents in our customer communication. We talk about moisture content balance, moisture content influencing factors, then drying, but how? And the logistics is point 6, which is also very interesting and important. And finishing with drying and solderability and further reading. So when is moisture in printed circuit boards critical? It's always the combination of humidity on the one side and thermal loads at the same time in the board. And thermal loads could be preheating before soldering processes, for example, or adhesive curing during SMD assembly, wave soldering, all types of solderings, especially selective soldering with very high impact of thermal load. And last but not least, rework and repair soldering. So these are often manual solderings, and you have to take care that the thermal stress must be controlled and minimized. And drying is absolutely necessary, especially for rework and repair soldering. So keep that in mind, please. And the effects of humidity on the PCB material are swelling on the one hand. So mostly all polymers are swelling if they are loaded with moisture. And moisture, on the other hand, could reduce adhesion forces at boundary layers. So boundary layers are the contact area between different materials, for example, flexible materials, gluing materials, copper material. And this is due to, for example, hydrolysis. So the adhesion forces are reduced. And combination with swelling, that's not that fine. So we usually don't have conditions as in a pressure cooker, but bubbly delaminations occur due to swelling and reduced adhesion forces. So in addition, cracks can develop as moisture reduces the critical fracture toughness and the Young's modulus of polymers. So crack propagation is favored by humidity in polymers. So let's have a look at some typical error patterns after soldering. On the left side, we can see a board which has passed some soldering tests, and you can see bright spots in large area. The second picture shows bubbles without copper in that place, so there is a separation inside the material, inside the PCB. The third picture shows us bubbles with copper, so we can clearly imagine that the big copper area um, had some humidity below, and so the bubble started there and made a delamination in the material. The right picture, the picture on the right side shows bubbles under copper, and this is the situation which is not that easy to find. So big copper areas and bubbles below that is yeah, kind of critical picture and error pattern. So now let's have a short poll, and I would like to ask you, what do you think, when are PCBs completely dry? Maybe before the washing process in our production, or on delivery to your site on picking from the stock after the first reflow process, or maybe never? So I now start the poll and ask you to make your decision in the blue screen. Okay, so first answers have arrived, and I will wait another few seconds. So please make your choice. Okay, so that looks great. That's fine. So I will stop in a few seconds and show the result of your choice. Okay, so now we can see most of you, exactly 50%, have chosen never, and that's quite the right answer. So it depends how much moisture we have inside the PCB, but we can never say a PCB is completely dry in normal usage. Okay, so 21% have chosen after the first reflow process. So reflow process has a high temperature, but not that long duration that there could be a significant drying effect on the PCB. So we'll see that later. Drying needs time, and reflow process may, of course, dry the surface, but not inside the PCB a lot. And 21% before the washing process, before electrical test. No, at that point, the PCB has seen a lot of different liquid processes, and depending on the surrounding, there is already moisture in the board. 7% are thinking that on delivery the PCBs are dry. Sorry, but no. As already mentioned, PCB always has humidity inside depending on the surroundings, the ambient conditions. So you have to take care that the PCB is enough dry prior to your soldering processes, for example. So PCBs are not dry, completely dry on delivery. Okay, so thanks very much for the answers, and now let's have a look at some documents in customer communication. So here we can see, sorry for the German language, I could not find them in English language, but in Germany they're well known, these documents from the ZVEA. So caring for drying of PCBs prior to soldering, and as well storage conditions. So I show these documents only for the sake of completeness without going into the details. It is important to note at this point that the fundamental necessity of drying before soldering must be considered as a necessary measure for all PCB technologies. Conversely, it means in particular that delamination during soldering after moisture absorption in your production is not a reason for a complaint, and that drying is a fundamental process component of the further processing of printed circuit board. So that's important to know. You have to check whether you have to dry. If you don't need to dry, that's okay. But if you're, for example, working with flex and flex rigid material, it's generally accepted in the market that these type of PCBs have to be dried. Okay. So next we can see our documents in customer communication from Word Electronic Circuit Board Technology. We have different specifications, and I want to point out that we are talking of specifications, not recommendation. So we think you have to dry, and there are different drying instructions, one for offers and one for shipment. And the version for offers as an attachment also caring for the point copper layout. So we will see that this is really important in the following of the webinar. So these are specifications. So let's have a look at humidity content. So humidity content always is an equilibrium. Humidity is water in molecularly dissolved form, mostly dissolved in air. And we all have already experiences with humidity. For example, cold glasses fog up. So, and fog and cloud formation we can observe in the sky. Um, um, Formation of clouds as well as disappearing of clouds if the sun is shining on the cloud and the temperature is rising. So the air could take more water without formating clouds. So we can see that on the right side in this diagram. We can see the temperature of the air on the x-axis, and as more temperature we have, the more content of water we can dissolve in air. So reducing temperature means reducing the content of water in air. So achieving equilibrium requires sufficient time. So that's not a sudden thing. It takes time, and takes a lot of time sometimes. So if we are regarding PCBs, we are not talking about minutes or hours. We are also talking or more talking about weeks and maybe years. So that's a long thing, a long process to reach a equilibrium. And a new equilibrium is established through targeted changes in conditions. So it all depends on the conditions of the surroundings. And absorption and release of moisture or drying are reversible processes. So that's also important to see. So if you want to dry, that's our topic of today's webinar. If you want to dry, we have to change the conditions around the PCB. And then it takes time, and it's always an equilibrium we are talking about after the time of the changes. So let's have this diagram showing a stack up or layer stack of a PCB. And there are different actions taking place. So firstly, there is adsorption of humidity of water molecules. You can see here in the air, dissolved in the air surrounding the PCB. So there is adsorption at the barrier here. And this is another process is desorption from the surface. And in the equilibrium, the rate of adsorption and desorption is equal. So next and third, there is absorption and diffusion into the PCB. So depending on the um, situation where we have more humidity outside or inside, there is absorption and diffusion into the PCB, or diffusion to the surface and desorption in drying process, for example. What we also can see is that there is copper, and copper acts as a barrier for humidity. So this is important to see. There's no chance for the humidity to pass this copper layer, this closed copper layer. And that's important in the following discussion. So a printed circuit board always contains moisture in equilibrium according to the ambient conditions. And the adjustment of the equilibrium takes time, as I already mentioned, maybe weeks and years after reaching the equilibrium, depending on the construction, on the material, and of course, depending on the ambient conditions. And that's another important thing. Moisture accumulates preferentially at boundary layers. So regarding different material types, for example, flexible polyimide and then gluing and coverlay and things like that. These are all boundaries, and unfortunately, the moisture accumulates preferentially at these boundaries, leading to swelling, leading to reduction in the adhesive forces. So these are the reasons for problems if we then load thermal loads on the material. Okay. So what are the influencing factors on moisture content? So of course, storage conditions, drying conditions, packing. So standard packing is not preventing moisture to go through the packing foil. So most foils are transparent for moisture. So keep that in mind. That's another reason why PCBs on delivery are not totally dry. So of course, material is an influencing factor. And last but not least, the design. So we have already discussed about copper layers and transparency of copper regarding the moisture diffusion. So I know an example in automotive production where they introduced a drying process for a serious production, and they did not have rigid flex, but they used base material with an increased moisture absorption, and the design itself was critical in regards of having a heatsink glued on one side of the board. So a heatsink out of aluminum is also a barrier for passing of moisture. So keep that in mind. And regarding flex and rigid flex, of course, here the base material is polyimide, and this has a higher moisture absorption compared to FR4, for example, resulting in swelling in hydrolysis, as we already learned today. Of course. Okay, so I want to have another poll with you, and the question this time is, which cause has the greatest influence on moisture loss during drying? So we want to dry, but the question is, which could make a barrier for the drying? Base material, copper design, oven temperature, pressure, or vacuum, so the surrounding conditions, or drying time. So now I start the poll and ask you to make your decision again. Now you can see the blue screen, hopefully. And I will wait another few seconds. Looking forward to your decisions. Okay, so we are near to 60%, 70%. So wow, now we got the speed. Another few seconds. Okay, more than 80% participation. That's great. So thanks for that. I will now close the poll and show you the results. So the winner of today's poll is drying time, and you're not so um, wrong. Drying time, of course, is really important. We will see that afterwards. 21% for oven temperature and as well for pressure and vacuum. So that means the drying conditions around the PCB. That's also important. 16% base material. I've talked a lot about base materials and moisture absorption of different materials. Yes, but the winner or the real thing is I will show that afterwards is the copper layout. So just 11% voted for copper layout. So we will see that the copper layout is really that thing we have to consider. Okay. So let's move on. So here we can see a test design. The test design shows us for different sectors. Sector A without any copper. So the PCB is a double-sided PCB, and the copper design is the same on both sides, 1.6 millimeter thick. And the test procedure was as follows. The board was loaded with humidity, with moisture, fully loaded. Then there was a drying process at 120 degrees C. And then the humidity was measured in a depth of 0.6 millimeters. Sorry, I forgot to translate some sentences here, 2 points. So this was a test layout, as I already mentioned, and the measurement of the humidity was in 0.6 millimeter deepness. So that is a starting point, and we now can see what's happening after a drying time of 6 hours. So after 6 hours, sector A, so just base material without copper, dries evenly and quickly. And after 6 hours, less than 20% of the initial moisture content is still there. If we look the next situation, after 15 hours, we can see that sector B now has more or less the same situation as sector A in the half of the time. So sector B takes about twice as long for having less than 20% of the initial moisture content. And the next measurement was taken after 25 hours. And here we can see that sector C with 75% copper coverage takes about 4 times as long as the base material itself without copper. And next measurement was taken after 45 hours. So 45 hours, just a long time, quite a long time. And what you can see is that with the closed copper coverage, that sector D dries only from the edges. And even after 45 hours, the moisture content in the center has decreased only slightly. And such differences in copper coverage also exist in a single design, for example, in power or logic areas. So that's why I said the copper design is the most important thing in the drying process. And this is the responsibility for this is not with the producer of the PCB. So you can see there is a special situation we have to take care for. So that's why I decided to call that design for drying. So we know already a lot of different designs for test, design for reliability, design for cost, and things like that. But today we have to talk about design for drying, and the largest contiguous copper area is the critical dimension for the drying process. And full copper layers without openings, yeah, should be or must be avoided even on inner layers. Of course, we need large copper areas in the design, maybe for reference for critical signals or for power ground systems, where we like this capacitive effect. But in respect to drying, we need copper openings, and maybe you can remove just a few openings in the near of the critical signals or shift them by the necessary amount. Fact is that even small openings in the copper represent diffusion channels for drying. Without diffusion channels, there is a closed barrier for the humidity, and there could be no drying via this barrier. So it would take more time for the drying process, as we have seen in the test on the last slide. So now let's talk about equipment for drying. And I intentionally do not show the ovens, but the decisive parameters. And relevant for drying is temperature. Temperature has a high impact on the diffusion rate. So if you want to dry quickly, we have to rise the temperature for the increasing of the diffusion rate for the moisture to go outside to the surface and dissolve to the air in the oven. Another thing is the heat transfer. So we need the temperature in the PCB, not in somewhere in the oven, but we need it in the PCB. So vacuum ovens are not the best choice. Humidity content in the oven is also an important thing, as it's responsible for the desorption rate at the surface. So after the diffusion of the humidity to the surface, we need the desorption rate. And we can see some drying conditions on the diagram here. So these are the three different drying conditions. We have 45 degrees C, less than 1% relative humidity, 60%, 60 degrees C, and 130 degrees C. We have different specimen to be dried. We have a rigid board, 0.4 millimeter thick. We have flex, 0.3 millimeter thick. We have flex rigid. We have FR4 this time, 1.6 millimeter, and there's a component. We don't regard that for this discussion, but we can see the humidity has a big impact on the drying time. So there is a common drying process with 120 degrees C. So that's still below the TG of the material. So we can talk about drying, not tempering. So that's real drying and efficient drying in a circulating air drying cabinet. Vacuum, not that effective, as inside the PCB we have a solid material. There are no pores or holes or voids where the vacuum could be effective. On the other hand, vacuum has the challenge to make the heat transfer to the PCB. So that's not that good decision to use vacuum ovens. Drying storage, on the other hand, drying storage cabinet is really suitable. Normally drying at elevated temperature, 45 degrees C or 60 degrees C, but you have to consider longer drying times, of course. I know a customer with medical applications, and he told me that his basically storage is over 2 weeks in a drying storage cabinet before the placement and soldering, and that he's fine with that. And the drying time in his case is firmly planned in his schedule. So you need longer drying times, but that's really an option at that place. Or of course you can also combine a drying process in a circulating air drying cabinet with a following drying storage cabinet. So that's another really interesting point, to combine these two different drying processes. So how do we develop an efficient drying process? The process looks like that. On the right side, we have to determine the moisture sensitivity of the PCB. So which material is used, what's the material mix perhaps, thickness, is the design for drying okay in terms of copper design maybe, or heatsink application. Do we have edge metallization, supply and reference layers, hopefully with copper openings for the drying? Then we need to determine the drying profile. Which equipment do we have for drying? And of course, we have to use the series equipment, not just an oven in the lab. No, we need the series equipment for that determination of the drying profile. And then the determination of the moisture absorption after the drying under your individual storage conditions. So clarifications are: how much moisture has the PCB absorbed by that point? What thermal temperature stress do we want to apply? Is there multiple soldering process, for example? And next thing is, what moisture absorption does the base material or the material mix show? Is the design for drying okay? I already mentioned these points. And what time without moisture protection must be allowed? So if you take the PCBs out of the dry conditions to the shop floor, you should consider that there is humidity again, and of course there will be a new equilibrium. And normally it's agreed to have a maximum 2 hours without moisture protection on the shop floor. If you exceed these 2 hours, you should go into dry conditions again with the boards. And the logistics, I already started to discuss floor shop, and there are another few questions. Should you use a fan for the drying for the PCBs, or use a stack for the drying? If you use a fan, there's always a risk of bending in the fan, which is not that good for the population of the components, of course, and the soldering process. If you use a stack, you must ensure drying in the stack, so the PCB in the middle of the stack should dry sufficiently. Also, you should check for transfer pressure, so the boards are lying at a high temperature on top of each other, so there should be no damage between the boards. Do you have labels? Is there bleeding? And you should protect the surface of each board from damage, especially scratches. So another thing is, what about the documentation of the production? Do you have some charts you're accompanying the process? Is there a drying log? So this is always helpful, especially in the implementation of the process, to find failures or things that have not been observed correctly. And another thing is, how is your production organized? Is there a Kanban, for example? So that could allow to fill the drying oven if there is a space, so to have a continuous drying and usage process. So this is a picture. I want to point out some important things again. So this is a standard baking oven from the kitchen, and we cannot really use that for drying PCBs. As I already mentioned, after the diffusion of the humidity to the surface, there has to be a desorption to make the PCB really dry. And if we think about baking in this oven, yeah, the cookies should not be that dry. So the humidity in this kitchen oven could not be removed out of the chamber. So that's not usable for drying PCBs. On the other hand, the stack is not really professional here. It's really thick and there is no protection for a PCB and so on and so on. So please do not use kitchen ovens for that process. Normally, industrial ovens have equipment for removing the moisture, and so that's really important at that point. And do not make pile too thick for even through drying of the stack if you're using stacks. Okay, last point, drying and solderability. Yes, we have normally we are using high temperatures for drying. So this is an aging of the PCB, and the solderability could be reduced. So you should check for that. A lot of PCBs, or most PCBs I know, which have to be dried, they use any surface, so electroless nickel immersion gold, and this solder surface is really robust and could also be dried several times and soldered several times. So that's a recommendation at this point here. Yeah, further readings. We have published an application note about moisture physics and process of drying of printed circuit boards. And you could get this brochure or this PDF, it's a digital version, this application note on our website, or drop me an email. I could send this. If you get in within 2 weeks, you will get the PDF presentation. There's a hyperlink between this picture. You also can use this. So inside the book, it's around about 32 pages. Again, in very deep description about the physics behind moisture, ending in an example for a drying process with pictures. So I really would like to recommend this application note to you.